So welcome you to this tutorial session or discussion hour. So if you have any doubts, please feel free to discuss them. Any doubts anybody has? Yes, anybody having any doubt? So let me just see, last time you were talking about invariance. I could not write down the solution, but let me see if I can produce a solution here. So last time what we were doing was, let me just check. Yeah. So can you see the screen now?
Yes, sir.
So what I had to show was that if theta hat is an MLE of theta, then G theta hat is the MLE of G theta. Now to show that G theta hat is MLE of G theta, what you need to look at is you have to look at the induced likelihood function at the point G theta hat x, and then you have to show that this is maximum, right, at G theta hat x. So I look at the definition of Lx star G theta hat x, which is supremum over all those theta belonging to theta, such that G theta is equal to G theta hat x, right, Lx theta. That is a definition, right, because Lx star eta was nothing but, what is the definition of Lx star eta? Supremum over all those theta belonging to theta, such that G theta is equal to eta of Lx theta, right? Now here in place of eta, you have a theta hat x. So it is supremum over all those theta belonging to theta, such that G theta is equal to G theta hat x. This is okay. Now, one thing you have to realize is theta hat belongs to this set. This set which we are talking about over here, in this set, theta hat belongs, right? Because if for theta hat, to show that theta hat belongs to this set, what do you have to show? To show that theta hat belongs to this set, that means theta hat satisfies this property. That means G theta hat should be same as G theta hat, which is always true. So theta hat always belongs to this set. Now, if theta hat belongs to this set, that means, and I'm taking supremum over whole set, so this supremum is always greater than or equal to Lx of theta hat x. Is that okay? Because theta hat x belongs to this set, and you're taking a supremum here over all that set. So this quantity would always be greater than or equal to. So this would always be greater than or equal to L minus x subscript x, and so theta hat is that okay?
Yes, sir.
Okay, up to this point. But theta hat x is a, no, these are likelihood function. Theta hat x is a MLE. So it maximizes the likelihood function. So that means this is same as supremum over theta belonging to theta of Lx theta.
Theta.
So that is what I do in the next line. So this is same as supremum. I think it doesn't take the supremum. So let me write down just supremum. Supremum minus. Yeah. So this is same as. So this is equal to supremum minus bracket theta, capital theta, such that yeah, supremum over theta belonging to capital theta, right? That is what it is. Right? Supremum over theta belonging to theta of L minus X. Is that okay up to this point?
Yes, sir.
Okay. Now what I do is now this is supremum over whole set theta, right? Now I partition this whole set theta into smaller orbits. So I look at first all those theta such that g theta is same as eta for some. So first I fix eta over here. So what I do is I do it over orbits. So what I do is I look at, because g may not be 1 to 1. So I look at all those theta such that g theta is eta, and I look at the supremum over this orbit. And then I take the supremum over all the orbits, right? So is that okay? So it's like saying that if you have to find a maximum, first you can find the maximum of each row, right? And then you can find the maximum of these rows, right? That is what you do. So exactly that thing over I'll do over here. It is a supremum over whole theta. So what I'll do is I'll first find the supremum over orbits, which are like rows. What would be that? What would be the supremum over orbits? So that means collection of all those theta such that g theta is equal to eta. Eta is fixed. So eta is could be ith row or ith row. So I look at supremum over only those theta such that g theta is same as eta. And then I look at supremum over all etas, right? That is what I do. So this is same as. So this is same as, yeah, supremum over, let me write down all etas. Is that okay? And then I look at, I'm varying eta. So here eta is now, eta is fixed. Now I look at the supremum over supremum minus, says that g of L minus X. Is that okay?
Yes, sir.
So it is the same thing which I explained. It is like first you fix the row. So first I fix the eta. I look at supremum over all those thetas such that g theta is same as eta. So this is supremum over all those theta such that g theta is same as eta. Now I keep varying this eta. So it is like varying those rows. I look at the maximum over all rows. So supremum over eta. Okay. Now so I am done now. Right. So now this quantity, because these are supremum over all eta, supremum over all eta would always be greater than or equal to supremum over a fixed eta. So this would always be greater than or equal to over a fixed theta. So I can just put this quantity. And now this happens for all etas. Whatever eta you take, supremum over all etas is always greater than or equal to for a fixed eta. And what is this? This is nothing but Lx star eta, right? This quantity is nothing but Lx star eta. So what you have shown is Lx star g theta hat x is always greater than or equal to Lx star of eta for every eta. Right? And that proves. Is that okay? Is that clear?
Yes, sir.
Okay.
Sir, in the asymptotic confidence interval, so can you please show the form of the confidence interval? Because in the lecture video, I am confused about root over I theta naught, whether it is on the numerator or it will
Let us
go
see.
in the denominator.
So you are saying let me see. Let me go to the lecture notes. I think that would be better. Can you see it now?
Yes, sir.
Asymptotic confidence intervals, right?
Yes, sir.
What we know is root n theta n hat star x minus theta naught goes in distribution to normal 0 1 upon I theta naught. Is that okay?
Yes, sir.
This part is okay. Now for any given alpha belonging to this thing, so that means root n theta n at star x minus theta naught. Oh, this you are mean to say. This should be in the, yeah, this should be in the,
Yes, sir. This should be in the denominator, in numerator.
yeah, numerator. There is a, because it should be 1 upon root of I theta naught, right? So it should be,
Yes, sir.
so there is a typo over there. Yeah, you can correct that.
Okay, sir. Yes.
Yeah. Anything else? Any other doubt anybody has?
Sir, in that theorem where you first give us three assumptions, where you were stating that probability that theta hat n star is a local maxima, that probability is tending to 1. Can you just means go through that? Yeah, that part I am unable to understand actually.
So this is all about, you see, what happens is, if you recall even your BSc days or while you are doing your last course, you routinely find out the maximum likelihood estimator by differentiating the likelihood function, right? And
Yes, yes.
you hardly cared about checking whether it is a local maxima, global maxima or not, right? You only seeing the critical point. Critical point is where derivative is zero. Right? Now the question is, if that is the case, how do you guarantee that the solution of this equation, which is likelihood equation, is equal to 0? Any root will be maximum likelihood estimator, or it will converge in probability to the true value of the parameter. So I'm trying to look at, suppose I don't want to go for a second derivative test, and I want to see what is the behavior of solutions of this equation, right? So that is what we are trying to study over here. So the first theorem which we did in this direction was, yeah. So the first says suppose certain assumptions are satisfied. Those are basically the regular conditions. Theta is differentiable. Then there exists a sequence theta hat star x such that probability that theta hat star is the root of equation is 1. So what it says is, under those conditions, the likelihood equation will have a root that probability is 1. as n goes to infinity. So asymptotically, there will always be a root of that equation. Is that okay? That is what it says. Because when you are looking at the critical point, what is the guarantee that there is a root? Maxima minima comes secondary. First, you want to guarantee whether it has a root or not. So this only guarantees the root. That means as n goes to infinity, probability that this likelihood equation will have a root, that probability goes to 1 as n goes to infinity. Is that okay? That is the first point. So once you know that asymptotically under certain regulatory condition, the likelihood equation will always have a root. What is the guarantee that such a root would be a maximum or even a local maximum? So it says there will always be a sequence which will correspond to a local maximum. That probability would be a 1 as n goes to infinity. Not only that, such a sequence will converge in probability to theta. So what this result is saying is, because your curiosity is, you see, I'm just looking at the solution of that likelihood equation. Now that likelihood equation might have a unique solution, might have more than one solutions, and so on. Even if it has unique solution or more than one solutions, what is the guarantee there will be a local maximum? It might not have a local maxima. It may be just increasing throughout. This theorem guarantees that whatever may be the case, if those regularity conditions are satisfied, then there will always be a root. Of course, this root is depending on n, and that is why we have written down this as a sequence. There will always be a root of this likelihood equation with probability 1. And such a root would be a local maxima with probability 1. Not only that, such a root would be consistent for theta. That is what it says. So that means likelihood equation under certain regularity condition will always have a consistent root, which would be local maxima. That is what this result is saying. Right? Nothing more. It doesn't say that this would be maximum likelihood estimator. It only says Lx prime theta is equal to 0 will always have a root which is a local maxima and which is consistent.
Achha.
It only says that. But one thing you can always say, that if you prove that your likelihood function has a unique root, then this theorem tells you everything.
Yes.
As a unique root, then it is talking about only that root only. Then it says, as a unique root, then such a thing would be a local maximum and it would be consistent. So,
Yes.
so as a corollary of this theorem could be that if your likelihood equation has a unique root, then that root would be maximum likelihood estimator. Because the local maxima, and there is only, if it is differentiable at the point of maxima, derivative has to be 0 if it is an interior point. So it would be a maxima. Not only that, it would be consistent. Right? So for example, in the normal case, all these assumptions are satisfied. Right? So I'm giving you an application of this result. For the normal distribution, so let us look at normal theta 1. Is that okay?
Yes, sir.
Normal theta 1, all those regularity conditions are satisfied. As I have told you, normally these exponential families are very nice families of distributions. And then all these regularity conditions are normally satisfied. So normal theta 1, this is satisfied. I look at the likelihood function for normal. It is 1 by root 2 pi to power n e to power minus 1 by 2 summation xi minus theta whole square. I take the derivative and do it. And I see that likelihood equation, does it have a unique solution or more than one solution? Whatever. It has a unique solution or more than one solution?
For a normal theta 1, it has a unique solution.
It has a unique solution.
Yes, sir.
So just by Lx prime theta is equal to 0, you solve theta is equal to x bar is the unique solution. This result says that x bar would be the maximum likelihood estimator and it would be consistent. You don't have to go for a second derivative test.
Yes, sir.
From this result itself, because it says if there are more than one root, then only there is a problem, because then you do not know which local maxima you have to consider.
Okay.
Right? So that is the main. So this theorem as such does not give you a consistent estimator. It only says that if you look at the solution of a likelihood equation, there'll always be a one solution which would be consistent and would correspond to local maximum. But suddenly, if likelihood equation has a unique root, then it tells you everything. Then such a unique root would be the local maxima, and since it is local maxima, it would be unique and so it would be maximum, and it would be consistent. Right? So that is what possibly when I go into the next theorem. So that is what this remark says. If you read this remark, in case of multiple roots, the equation Lx prime theta is equal to 0. The above theorem does not say which sequence of roots of the equation should be chosen to ensure consistency. It says there will be one which would be consistent. Forget about maxima, even about consistency. It only says there will be one such root which would be consistent. Second point of the remark says the above theorem does not guarantee that for any given n, however large, the likelihood function has any local maxima at all. Right? It only says asymptotically there would be such a root would exist.
Means sir, here given n means that is n is supposed here to be finite, right?
Yeah.
Okay.
N would be fixed.
Hmm.
For any fixed n, there may not be any root. It is only asymptotically there is a root. Limit n going to infinity, probability that theta n at x would be a root. That would be one. Is that
Yeah.
okay?
Yeah, it's clear now, sir.
And if for every n and x, this is what very important thing, C part, if for every n and x, the likelihood equation Lx prime theta is equal to 0 has a unique root, then the above theorem guarantees that it will be consistent, and with probability 1, it will maximize the likelihood function, will be called MLE, right? So this is what it says. Is that okay?
Yes, sir. Yes.
So normally this result is very useful when you have a unique root. Okay?
Yes, sir.
Oh, I was not sharing the screen, right? Did I share the screen or not?
No, sir.
Okay, shall I repeat it or?
No, sir.
No? Yeah, so it only tells you that if you look at that part ABC, it says that there'll be, let me just do it. I can do it quickly because I've explained everything. I can do it quickly. Yeah, so if you look at this part, suppose that assumptions A1, A2, A3 are satisfied, which would be the case in the exponential case, and f theta x is differentiable, then there exists a sequence theta n at star x. And sequence because it depends on a n. So there'll always be a estimator theta n at star x such that probability theta n at star is a root of this equation that goes to 1. Right? So asymptotically, likelihood equation will have a root. Asymptotically in the sense as n goes to infinity with probability 1. And with probability 1, such a root would be a local maximum. That is what it says as n goes to infinity. And not only that, such a root would be consistent. So as a consequence, you get these remarks, which says in case of multiple roots, the equation Lx prime theta is equal to 0. The above theorem does not say which sequence of roots Lx prime theta is equal to should be chosen to ensure consistency. The above theorem does not guarantee that for any given n, however large the likelihood equation has any local maximum, because it only says that probability that limit n going to infinity, that probability goes to 1. So asymptotically only you can say that there will be a root, but for a fixed n, it doesn't guarantee any root. Second thing is, if for any n x the likelihood equation has a unique root, then the above theorem guarantees that it will be consistent and with probability tending into 1 will maximize the likelihood function, that is, will be the ML. Right? So this is what this corollary says under the assumption of last theorem. Suppose that the equation Lx has theta unique root for every each n and x, then theta n star is consistent for theta. Moreover, with probability tending to 1, theta n maximizes the likelihood function. Is that okay? Is that clear now?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. Anything else you want to ask?
Sir, can you discuss the part C of problem 19 of assignment number 5?
Problem C of
19.
19. Let me see. Problem C, right? So it says
Yes, sir.
find MME, say delta n based on xi square. So it says find MME based on xi squares, right? Not on xi. And so that it is a can. Compare the asymptotic variance, its asymptotic variance with that of 1 upon n mod of xi. I think similar kind of a thing we gave in the exam, except that there it was normal. Find the LRE and MRE of this thing asymptotically. Says 19C. So So first, when I try to find out the method of movements based on xi square, then I know that my data is x1 square, x2 square, and xn square. So I put the sample movements of x1 square, x2 square, and xn square is equal to population movements. So I first calculate what is the population movement of x1 square. So first I need to find out what is the expected value of x1 square. Right? Expected value of x1 square, you can find it out, which is how much? 1 upon minus infinity to infinity x square e to power minus mod of x by theta and 1 by theta and d theta whole square, which turns out to be 2 theta square. Is that okay?
Yes, sir.
So what I have to do is I have to put 2 times estimator square, because theta square, 2 times delta n1 square is equal to the first movement based on x1 squares, which is 1 upon n summation xi square. Is that okay? So my delta n1 turns out to be 1 upon 2n summation xi square, which I can write down as root t bar by root 2, where t bar are xi squares. So mean of xi squares and their square root. Okay? That is what it is happening. So T1, T2, Tn are IID with expected value of T1 as expected value of x1 square, which is 2 theta square. Variance of T1 is same as variance of x1 square, right? Which is 24 theta to the power 4 minus 4 theta to the power 4, 20 theta to the power 4. So any doubt up to this point?
No, sir. But for calculating the variance, so
Right.
how to calculate that? By integrating, or there is some other method also?
Just see what is the distribution of a mod of x1.
It is
Just by looking at it, you can tell what would be the distribution of mod of x1.
it is similar to exponential, but
It is exactly exponential actually.
there is a half outside.
No, half, because the function is not 1, 1, right? So
Yes, sir.
half and half, both images will come and it will get added, right? So half would vanish. So it will be 1 by theta e to the power minus x by theta for x greater than 0,
Mm-hmm.
right? So that means your mod of x by theta is standard exponential.
Yes, sir.
Mod of x by theta is standard exponential is chi square on how many degrees of freedom? Chi square on 2 degrees of freedom, right? E to the power minus x density,
Yes, sir.
right? So mod of x1 by theta is chi square on 2 degrees of freedom, right? Yeah. So that means x1 square by theta square is square of chi square on 2 degrees of freedom, right? So that means x1 square by theta square is square of a chi square. So that means expected value of x1 square by theta square would be nothing but expected value of square of chi square degrees of freedom. And what is expected value of square of chi square with 2 degrees of freedom?
2. 2 it will be.
Variance of x1, which is 2.
Yes, sir.
It should be 4 in that case, right?
Variance should be 4. Expectation will be 2.
Expected, no, you see, what I'm saying is, what you get is a mod of x1 by theta, right? So mod of x1 by theta is standard exponential, right?
Yes, sir.
Density is e to the power minus x. Standard exponential is nothing but chi square on 2 degrees of freedom,
Hmm.
right? No, standard exponential is not chi square on 2 degrees of freedom, because e to the power chi square 2 degrees of freedom e to the power minus x by 2 comes. Chi square 2 divided by 2 is standard exponential, right? So standard exponential is nothing but chi square 2 divided by 2. Is that okay? Yes or
Sir,
no?
we can also use the properties of gamma distribution.
You can use the property of gamma also, that is not a problem. That also you can do. So because what you get is mod of x1 by theta is exponential, is z, which is exponential 1. So x1 square by theta is nothing but expected value of x1 square by theta is nothing but expected value of z square. Z square is exponential 1. What is expected value of z square?
Variance plus expectation square.
Z square would be gamma 3 would be 2.
2.
Right? So that is what we have got over here. X1 square by theta square is 2. So actually x1 square is 2 theta square. And that is how you get it. So this, what you are talking about, variance of x1 square? Variance of x1 square would be expected value of x1 to power 4. What is expected value of x1 to power 4? x1 to power 4 by theta to power 4 is z to power 4, where z is exponential 1.
Yes, sir.
Right? So expected value of x1 to power 4 by theta to power 4 is expected value of z to power 4. Expected value of z to power 4 is nothing but z to power 4 e to the power minus z dz, which is nothing but gamma 5. Gamma 5 is factorial 4, which is 24 theta to power 4 comes. Is that okay?
Yes, sir.
Minus expected value of x1 square whole square, which is 2 theta square whole square, which is 4 theta 4. So this turns out to be 20 theta to power 4. Is that okay?
Yes, sir.
So by central limit theorem, you know that root n t bar minus mean of t bar is, which is 2 theta square minus 2 theta square, goes in distribution to z, which is normal 0, sigma square. Variance of t1 is 20 theta to power 4. So it is 20 theta to power 4. Is that okay? So t bar I have found it out. What I have to find is, I have to find the distribution of root of t bar. So I use the delta method.
Delta method.
So root n, root t bar minus square root of twice theta square, which is root 2 theta, goes in distribution to h prime at the mean. H prime is square root 2, so 1 by 2 root x. So 1 by 2
Yes.
at the mean, which is 2 theta square. So 1 by 2
Okay.
theta square z, which is nothing but normal 0. This was already 20 theta to power 4. So here it will come 4 to 8 theta to power square. Right? So theta square, and this becomes 5 by 2 theta square. Is that okay? So root n delta n1 minus theta. So I multiply both the side by, divided by both the side by root 2. So root t bar by root 2 becomes delta n1. Root 2 theta by theta becomes, goes in distribution to root 2 times this distribution. Right? Root 2 times this distribution, normal 0, 5 by 2 theta square would have a normal 0. And yeah, 5 by 4. I'm dividing by root 2 because here, right?
Yes, sir.
5 by 4 theta square. Right? So delta n1 is can. Is that okay? Now I look
Yes.
at root n delta n2 minus theta, which is root n y bar. Right? Y bar is mod of xi. Where is it? And expected mod of y is theta, which is root n delta y bar minus theta, goes in distribution to normal 0 theta square. Is that okay?
Yes, sir.
This is also can. You can consider the asymptotic derivative efficiency of delta 1 related to delta 2, which turns out to be 4 by 5, which is less than 1. Asymptotic variance of delta n1 is 5 by 4 theta square, which is greater than theta square. this, which is equal to asymptotic variance of delta n2, which is attains the Cramer-Hall over bound, which is theta square. So delta n2 is asymptotically efficient, whereas delta n1 is not asymptotically efficient. Is that okay? Now this you can use that result about the moments. N times variance of delta n1 is same as h prime n by 2 limit of variance of root of t bar, which is same as n by 2 20 theta to the power 4 n by plus order of n square. So this is what it is. Is that okay?
Yes, sir.
Now the only thing over here is if hx is equal to root x, you have to only verify that fourth moment of h square is bounded, because for variance you need the moments of h square to be bounded. So h square would be x, the fourth derivative of h square would be 0, right? So that is not an issue. Is that clear?
Yes, sir. But sir, here both the estimator are unbiased or biased?
You see, one can look at that. You can directly see from here, no? Your method of moment estimator always gives you unbiased estimator, right? So that would always be
Yes, sir.
right. Now the second one is also unbiased, right? So both are unbiased. That is not an issue. Right? That moments you can find out directly, no?
Yes, sir. So for the for computing the ARE,
Mhm.
so cannot we compare their variances directly?
That is what we are doing, no?
Yes, sir. But here we also considering the order, that formula that you gave. I'm telling that as we have already computed the distributions, so cannot we use the variances?
You can find out directly also. You can find it out directly also. But this normalization still you will have to done, right? Because variance will always go to 0, because they all are consistent estimators. So this normalization
Yes, sir.
and suitable factor of n will you have to do. Is that okay? And this factor
Yes, sir.
is same for both the estimators. If it is n for one estimator, it should be n for the other estimator also. Right?
So from the asymptotic distribution, can I compute the ARE directly?
Yeah, asymptotic distribution, that is what we are doing, no?
Yes, sir.
And delta n minus theta is normal 0 5 by 4 theta square. Root n delta n2 minus theta is normal 0 theta square. Efficiency of delta 1 related to delta 2 is theta square by, I think this is normally 2 power 1 by alpha, right? So alpha here is half. So it would be this square, right? If you see our notes, efficiency is good because it is a ratio of sample sizes. So alpha here is half. There I have used n to power alpha. So normally efficiency, if you look at that theorem, it should be 1 upon alpha. So alpha,
1 by alpha. Yes, sir.
so it should be 2. So it should be 4 by 5 square, right? Which is 16 by 25. Is
Yes, sir.
that clear?
Yes, sir.
Yes. Any other doubt anybody has? Yeah.
Hello, sir. Sir, in problem number 15,
Yeah.
the UMVV is x minus 1 x into 1 minus x by n square minus n.
Problem number 15, right?
Yes, sir. Can you explain the only the asymptotic means can consistent I proved it, and can you explain the asymptotic part?
So x is binomial and theta. Find the UMV of s theta. Is it can, right? That is what it is asking for, right?
Yes, sir.
Problem, no? So let us go to 15. Yeah. So finding this UMV is okay. X into n minus x upon n into n minus 1. Right? Is that okay?
Yes, sir.
Somehow I have to write down this x in terms of x bar. Right? Now in the binomial case, if x is binomial and theta, as x can be written as summation I is equal to 1 to n xi, where x1, x2 are IID binomial 1 theta. Is that okay?
Yes, sir.
So the reason is, although I know x, but x can always be written as a sample sum of IID binomial. So this is same as Cn times n I take outside, right? This x by n becomes x bar. When I have taken n outside, it has become 1 minus x bar. And what is a Cn? Yeah,
Here, sir, Cn is 1 minus 1 by n.
minus 1, right?
Yes, sir.
Which is 1 plus 1 by n plus order of 1 by n square. Is that okay?
Yes.
Okay. Now by certain limit theorem, I know that root n x bar minus theta goes in distribution to normal 0, because theta is the mean of xi's. Normal 0, variance of xi's. Variance of xi's is equal to xi's are IID binomial 1 theta, so it is normal theta into 1 minus. Is that okay? Now what here I have is Cn x bar into 1 minus x bar. Right? That is an issue. So first I apply the result to hx equal to x into 1 minus x. Is that okay? Is that okay?
Yes, sir.
Find out the distribution of x bar into 1 minus x bar. So here h prime x turns out to be 1 minus 2x. Right? So what I know is root n h of x bar minus h of theta goes in distribution to h prime of theta times z. Is that okay? But note that h prime theta is 1 minus 2 theta, which would be 0 if theta is half. So that means if theta is half, I'll get here 0 times z. So it goes in distribution to something 0, which is convergence in probability. Right? So that is why that case I am considering separately. When h prime theta is 0. So that means I am first considering the case where h prime theta is not 0. That means theta is not equal to half. If theta is not equal to half, then root n hx bar minus h theta by the delta method goes in distribution to h prime theta into z. H prime theta is 1 minus 2 theta. So h prime theta z goes in distribution to, because z was normal 0 into theta into 1 minus theta. So h prime theta z will go to normal 0 h prime theta whole square into theta into 1 minus theta. So it says root n x bar into 1 minus x bar minus theta into 1 minus theta goes in distribution to z1, which is normal 0 theta into 1 minus theta into 1 minus 2 theta whole square, because h prime theta is 1 minus 2 theta. Is that clear up to this point?
Yes, sir.
Okay. So now I have to look at what is the distribution of root n Cn x bar minus 1 minus x bar minus theta into 1 minus theta. Because Cn is going to 1, right? So I would expect, even if I put here Cn, things would not change much. So I'm putting Cn over here. So what I do is, here I add and subtract x bar into 1 minus x bar, right? So it becomes root n x bar into 1 minus x bar minus theta into 1 minus theta. Then I have to subtract x bar into 1 minus x bar, so that will give me Cn minus 1 x bar into 1 minus x bar. And what is the Cn minus 1 into x bar into 1 minus x bar? 1 by n plus order of 1 by n square x bar into 1 minus x bar, which is same as order of 1 by root n, because root n was also there. Is that clear?
Yes, sir.
Because I have added and subtracted just over here x bar into 1 minus x bar. So when I added x bar into 1 minus x bar, that got combined with theta into 1 minus theta, subtracted it, then I get Cn minus 1 x bar into 1 minus x bar into root n. So I have to see what is root n into Cn minus 1 x bar into 1 minus x bar. X bar into 1 minus x bar comes, so I have to only see what is an order of root n into Cn minus 1. Cn minus 1 is 1 upon n plus order of 1 by n square. So root n, Cn minus 1 is 1 by root n plus order of higher orders of this thing. So which is same as big O of 1 by root n. Right? Big rho of, that means it goes to 0. because if big O of 1 by root n, so what does that mean? So this quantity is going to 0, right? This quantity big of 1 by root n has to go to 0 because this is 1 upon root n plus something, and 1 upon root n goes to 0. This goes in distribution to something, this goes in probability to something, 0. So the sum will go in distribution to this quantity only, root n x bar into 1 minus x bar, which is normal 0 theta into 1 minus theta into 1 minus 2 theta whole square. So that means root n delta minus h theta goes in distribution to normal 0 theta into 1 minus theta 1 minus 2 theta whole square. Is that clear? Is that clear now?
Yes, sir.
Okay. Now theta is equal to half case I have to consider separately, because for theta is equal to half, h prime theta is 0. So this will be a convergence to a in probability, but I want a convergence in distribution. So that suggests I should go to the second order derivative in the Taylor's expansion. So in that case, I know that n times, here it becomes n, hx bar minus h theta goes in distribution to h prime theta by 2 z square. So I'm using the delta method when h prime theta is 0. Is that okay? So that means
Yes, sir.
n times x bar into 1 minus x bar minus theta into 1 minus theta goes in distribution to what is h prime, h double prime theta? Minus 2. Minus 2. So minus 2, so it becomes minus z square. So that means n times Cn x bar minus 1 minus theta into 1 minus theta. I again add and subtract the same thing. So it goes over here. Now because of this n over here, you don't get a 1 upon root n over here. And n gets cancelled and you get only 1. Right? Now this goes in distribution to this quantity minus z square that you know. Where does this goes to? This goes to 1. And this goes in probability to theta. So x bar into 1 minus x bar will go in probability to theta into 1 minus theta. So this whole will go in probability to theta into 1 minus theta. This goes in distribution. So by Shlesky's lemma, everything will go in distribution to theta into 1 minus theta minus z square. Right? So I can take theta into 1 minus theta outside. So 1 minus zeta. So this is theta into 1 minus theta 1 minus chi square. Is that okay?
Yes, sir. Thank you, sir.
So for theta is equal to 1/2, you don't get a asymptotic distribution to be asymptotic normal. So you cannot say that this estimator is can. Okay? So I think we have finished the timing. So it's almost over. So we'll meet tomorrow. We can discuss either the same thing or the invariant hypothesis testing. So see you tomorrow. Anything else you want to ask?
Sir, for the syllabus in NSEM.
But very few of you are present today, right? I just see very few. So yeah, have you decided something about the syllabus?
Sir, could you please reduce the syllabus a bit so that in the NSEM?
I'll ask suggestions from you people. So do you have something to suggest?
Sir, can the first part, that the limit Bayesian part and the minimax. So can you?
Yes, sir.
That you don't want to. So you want basically the post midsem, right?
Yes, sir.
Yes, sir.
Post midsem would be a what?
Asymptotic estimators and then the testing part.
Asymptotic and testing. Okay, so that's okay because it's very unusual. I don't want to burden you. Had it been a normal semester, I would not have really conceded to your suggestion. But since it's a difficult time for all of us, it's okay. As far as learning part is there, that anyway I have taken care of. I have delivered, I've tried to give you all the lecture notes and everything. So learning part is anyway taken care of. It's only the evaluation part which we may be lacking, but considering the fact that these are very unusual times, and I don't want to put you all into a lot of stress. So I can do that. I can ask things in the end sem only for the post midsem, which is basically, let us not call it a post midsem, but let us call it asymptotic.
Yes, sir.
And
Yes, sir.
so we'll again re-emphasize it tomorrow, but tell others to attend at least tomorrow's session. All right. So that
Sir, one thing, sir, as you give us the solution of assignment 5, so I don't think there are too many questions regarding the assignment 5.
so
No, means I am telling the fact.
to ask, right?
Yes, sir.
Questions to ask from the assignment number 5, right? That is what you're saying?
Yes, sir.
No, questions are unlimited, right? Questions can be asked. That is not a problem. So we'll discuss again it tomorrow, right? Because when more students are there, so tell others, because I don't want to hear excuses. A lot of you have a habit of at the last moment and saying, sir, I was not present in that session and then I didn't know and all that. So tell others to be present tomorrow so that we can finalize in tomorrow's session what will be the final session. Is that okay? Okay.
Okay, sir.
Yes, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.